and welcome to this video on Kinetics. This is for OCR salters. My name is Chris Harris and I'm from AlleryTutors.com, and like I say, this video is mainly a revision video and it's going to go through the Kinetics topic for the salters spec. It's generally designed just to give you an overview of what you need to know for the exam. Now, the slides that I've got here, they are available to purchase. If you just click on the link in the description box, you can get a hold of them there, but they are great value for money and you get a discount by buying the whole series for the whole of AS. Really help you to get that top grade that you need, and a great supplement to the revision that you may already have got already. Okay, like I say, the points, as you can see on here, they match the OCR salters specification, and they're taken from that syllabus, so that's what they're matching. So if you're doing salters, this is perfect for you. Okay, so we're going to look at rate and collision theory. So for a reaction to occur, particles must collide. And so we're going to look at, obviously, the rate of reaction, which is how fast something happens. So the official definition for a rate of reaction is the change of concentration or amount of a reactant or product per unit time. Now that unit time could be in seconds, it could be minutes, it could be hours, doesn't really matter, but normally it's per second. And rate is the amount of time, the amount of reactant used or the amount of product made, depending on what we're looking at, divided by time. Now, particles move all the time and they collide into each other as well, but most collisions actually don't lead to reaction. Some of these particles, they just hit off each other and they bounce away from each other. So collision theory, so for a reaction to occur, the particles must collide in the right direction. Okay, it's really important. And they must also have the minimum amount of kinetic energy for that reaction to occur. If they don't have the right amount of energy, or they're not hitting each other in the right place, then you won't get a reaction, and they will collide, but they won't react. So I'm just trying to distinguish that difference between reaction and collision. Okay, activation energy. Basically, this is the minimum amount of energy required for a reaction to occur. Okay, and you're going to see this quite a lot throughout this video here, knowing what an activation energy is. But you can see we've got an energy profile diagram, and this is basically showing the energy changes in a reaction. So you can see here we've got enthalpy here along the side, and we've got reaction progress along the bottom. You can see here we've got reactants on the top here and products which are lower in energy than our reactants. Now, molecules at this point here, their bonds are stretching. They have a little bit more kinetic energy, so we've heated them up, and that's all they're doing. You can see here from the reactants up to this, the top line of the energy profile, this gap is called the activation energy. And so this is always between reactants and the top of the profile. So you're always looking out for that particular part there, and that's called the activation energy. Basically, at the top of the profile, the bonds have sufficient energy for them to break. So they have enough energy for them to break and actually collide. Now, reactions that have low activation energies, these need less energy to break the bonds. And normally, obviously, we're looking at heat energy in this case. And obviously vice versa. So if they have a large activation energy, you're going to need a lot more energy to break them bonds. Now we're going to look at something called the Maxwell-Boltzmann Distribution. Now you've got to be really careful with the different parts of this graph. Basically what it shows you is the energy in gas particles. Okay, so particles, let's say we've got a sample, we've got a box, we've got particles in that box. They're all moving at different speeds. Okay, they don't all have the same speed. Some are slow, some are quick. And they have different amounts of kinetic energy. That's moving energy. Now we can plot this on a graph. We get something called a Maxwell-Boltzmann distribution. So let's have a look at it here. We've got the number of molecules, as you can see here. There's the number of molecules going up and kinetic energy going along the side. You can see we've got this funny graph, kind of really steep initially, peaks here, and then slowly drags down towards the end. These graphs always start at 0, 0. So basically what we're saying is no particles have zero kinetic energy. So we always start here. Okay, so we have even some particles have some kinetic energy. And the total under the graph, under this curve here, so this area here, is equal to the total number of molecules. Now when we change the temperature of these things, you'll be able to see that actually the area under the curves are always the same. They might look a different shape, but the area is the same. Okay, this bit where the peak is, this is the most likely energy of a particle in a sample. Okay, so this is what the, if we had to do a sample of these, this would be the energy that most of the particles will have. The one slightly to the right of this peak is the mean energy the particles have. You can't get them too mixed up, they are different. Okay, so the most likely energy the particle will have, this is the mean energy, which is always slightly to the right of this peak. And this bit is the activation energy. It's always to the right, and you can see here we've got this yellow line symbolizing the activation energy. Now these particles in this part of the graph, these have very little energy. They're moving pretty slowly. The ones in the middle, these have a moderate speed, and obviously the ones over here, in this yellow section here, these have enough energy so they can react. In other words, they've got energy greater than the activation energy. And you can see here, any particles with energy up here will react. So they'll collide and react. Okay, so let's have a look at what affects rate. So temperature affects the rate of reaction. So particles on average, they have more kinetic energy when they're heated. Okay, remember this is on average. Not all particles will have more energy, but just on average, we've got a lot more having more energy. A larger proportion of the molecules will have energy greater than the activation energy when we've heated them. And you can see we've got this red line on a graph that's just been drawn there. This is showing a higher temperature. And you can see here that we do have a larger area now of particles, or more particles with energy greater than the activation energy, and that's why our rate of reaction increases. There's a few other points to point out as well. So you can see the curve is slightly shifted to the right. So we've got most particles have energy greater than the activation energy, which is there. The area under the graph is actually the same as the one in the white line. Okay, so we have got a higher, slightly elevated graph, but the peak is lower, so the area is the same, and the area under the curve beyond the activation energy, like I say, does increase when we heat that reaction up. Now we can do it the other way as well. Obviously we can cool it down, we decrease the temperature, we have a smaller proportion of molecules with energy greater than the activation energy, so we've got a smaller area beyond that activation energy, and this is the blue line here. Okay, this is the blue line there. So again, some very important points to notice. When we've cooled or reduced our temperature, the curve shifts to the left. You can see here now that peak is much further to the left compared to the other ones. The peak is a lot higher, so many more particles have energy that is lower than what it was before. And but crucially, the area under the curve is actually still the same compared to the red, white and blue. It's always the same. But the area under the curve beyond the activation energy, you can see this is much lower, with a much smaller area there beyond the activation energy. Okay, so why do we get a faster rate of reaction when temperature is increased then? So what they do when we heat these particles up, they move around a lot more because they've got more kinetic energy. When they've got more kinetic energy, they'll collide a lot more, and this is why the reactions happen a lot faster at higher temperatures, because they're moving around a lot more. And the combination of two things actually increases this rate of reaction. So we've got more collisions because they are obviously moving around faster, and we've also got more energetic collisions, as obviously demonstrated in your Maxwell-Boltzmann distribution. And this basically means that a small increase in temperature will lead to a large increase in rate, because we've got two things here. So more collisions and more energetic collisions. So this double effect really does increase the rate of reaction when we make a small increase in temperature. Concentration and pressure, these also affect the rate of reaction as well. So pressure, for example, if we increase the pressure, this will increase the rate of reaction. The particles are much closer together, collide more often, we've got more frequent collisions and a higher chance of a reaction. All of these words underlined here are key words. Make sure that you're writing them down in your answers, okay, when you're describing pressure affecting the rate of reaction. You can see here we've got two diagrams, low pressure here, high pressure here. In this case, we've just used the same number of particles, but we've actually squashed the container that we've put them in, so these are effectively high pressure. Concentration, very similar to pressure, except obviously this is to do with solutions. So the particles are still much closer together, collide more often, more frequent collisions, and a higher chance of a reaction. And this is true when we've got a higher concentration of a substance. And you can see I've drawn a diagram to show a low concentration, and obviously we've got a higher concentration here more red particles here, so there's a higher chance of them colliding into each other and obviously forming a reaction. Catalysts, they also affect the rate as well. What they do is they increase the rate of reaction by providing an alternative pathway that has a lower activation energy. And remember, catalysts are chemically unchanged at the end of the reaction. So even if they've been used up initially, they're reformed at the end. And you would have seen that in the radical reactions for ozone in particular, or the formation of a haloalkane from an alkane and a halogen. That also is a catalyst because obviously the chlorine radical is reformed. Now, catalysts are used to speed up a specific reaction. Obviously, as you've seen before, we use different catalysts used for different reactions. We don't just have one catalyst. And they're basically used to make that product faster. Okay, these can be used to lower the temperature as well, because remember, if the activation is reduced, activation energy is reduced, it means we need less money to effectively heat that up, and less energy as well. Okay, and obviously if we make the product faster, that's great, because as we say, time is money in these types of reactions. Now, this is an example of a catalyst called zeolite, as you can see in this picture here. Large surface area, loads of micropores in this, and that surface area rapidly increases the rate of reaction. So when we're using catalysts, we do try to use them with a large surface area, particularly obviously if it's a solid catalyst, like this one here. Now you'll see in a minute, we've got two types of catalysts called heterogeneous and homogeneous. This would be an example of a heterogeneous catalyst if it's placed in a reaction with liquids or gases. Okay, so how does a catalyst affect rate? We're going to look at both diagrams here. So we're going to look at the Maxwell-Boltzmann distribution first. And you can see here that the catalyst has actually lowered that activation energy. So we've shifted that further to the left. So we've got more particles now with enough energy for them to react. So you can see here that we've got an activation energy with no catalyst, and here's the activation energy with a catalyst shifted to the left. We now have a larger area under this graph here. The energy profile diagram, well, same thing. You can see here that we've got our activation energy with no catalyst. There's our reactants going to our product. Remember, this was the activation energy, these two yellow lines. If we add a catalyst in, though, it lowers that activation energy. So we have a different profile. There it is there. There's the alternative pathway. And you can see this alternative pathway does have an activation energy that is lower. So less energy is needed for them particles to react. Okay, homogeneous catalysts are slightly different. So we've seen that energy profile there where we had that simple like curved line and we'd show in the activation energy. Now, catalysts can be described as homogeneous as well. So homogeneous catalysts, basically these are catalysts that are in the same phase as the reactants. Okay, so these are normally aqueous catalysts in aqueous reactants. So for example, you use sulfuric acid to make ester. So sulfuric acid is a aqueous solution, and so is your ester. So both of them are in the same phase, so we describe them as homogeneous. Enzymes in body cells, they're homogeneous as well. Remember, enzymes are biological catalysts, so these allow chemical reactions in your body to occur. Now, homogeneous catalysts, these form what we call an intermediate species. Okay, they behave slightly differently to heterogeneous ones. What they do is they combine with the reactants first, and then what they do is they then release themselves to form the product, but the catalyst crucially is reformed again, and you get this unique energy profile. So you can see here, we're going to show you this energy profile diagram. Okay, they actually have two activation energies, and like your heterogeneous one, which we'd seen before, where you just had one activation energy, so one profile, this one has two. So let's have a look. Here's our energy profile. Here's our reactants, and here's our products. Enthalpy along the side, reaction progress on the bottom. Now you can see this is the activation energy with no catalyst. This is very similar to remember the heterogeneous catalyst, the solid one, is just another single rise, but it's lower than that. But homogeneous catalysts form this intermediate. So they form this. It looks a bit strange, doesn't it? So this is the activation energy with the catalyst in the first step. You can see here that it is lower than the original one because it does lower the activation energy. But you've got this first one here. You form this intermediate, which is here. And then you can see that we've got, then it forms like the catalyst effectively releases itself from the molecule, it's reformed, and your product is formed. We can see the activation energy with the second step. So we've got 1, 2, with this double bump, okay, in here. So make sure you're able to draw this. Notice the second bump is lower than the first as well, okay, and this is the intermediate that's been formed. Okay, so remember that profile and make sure you know when to draw a homogeneous catalyst energy profile diagram. Okay, so how can rate be measured in experiments? Okay, we can basically measure how long it takes for a precipitate to form. This is great if our reaction does produce a precipitate. So, for example, we'd seen the one with the bond enthalpy of haloalkanes, and we used silver nitrate, and we've seen obviously the cream, white and yellow precipitate being formed. That would be quite good because we're monitoring the rate of reaction. So this is another one. Basically, you could put your conical flask, your reaction in there, time how long it takes for that cross underneath to disappear. Obviously, there is problems with this, though. It's difficult to know exactly when that cross disappears. It's best to use the same person to observe this cross disappearing so we don't have different ideas of when it actually has disappeared. Another one is the amount of mass lost as well. So reactions that produce gases, this is ideal for that. Basically, we've just put the reaction on a top pan balance and we measure the mass loss over time. Now, it's a fairly accurate method, but if the gas produced is toxic, you've got to do that in a fume cupboard, so you've got to be careful with that. Another one is you can measure the volume of gas that's produced. So this is another way of measuring the rate of reaction. Basically, we just have a reaction, we set it away, gas is produced, we have a delivery tube here into a gas syringe, and we're monitoring over time how long does it take to, or how much gas is produced, so to say, in 1 minute, for example. So we set the stopwatch away for 1 minute, see how much gas is produced after 1 minute, we stop after 1 minute and take a reading. And basically we can measure, obviously, how quick that gas is produced over a specified time. Other methods as well, so you can measure the change in temperature if it's a reaction that can change temperature and it's quite a wide ranging temperature. Measure the change in pH as well, so you can use a pH meter and we can monitor that. Measuring via a titration, so we take samples of the reaction at regular intervals. So in other words, we take a beaker or conical flask, set the reaction away, and what we do is we add a quenching reagent. It just stops the reaction, like freezes the reaction at that moment in time. We do a titration and work out how much of the product has been produced or reactant that's left. And obviously we can do that at every minute, for example, and do regular titrations and just record our results after each time. So we can do that as well. It takes a bit of setting up, that one, but you can still do it. Okay, so let's look at how we can calculate rate from a graph. So rate can be found from the gradient of a graph. And you can see here that we've got a reaction and we've got a volume of a gas produced in this example. So this is in centimetres cubed. And we've got time in minutes along the bottom. So the gradient is just the change in y over the change in x. And remember, this is y and that is x. So we're just measuring how steep that graph is. Now, the best thing to do is try and find the big section of the graph so you can work out the gradient. The bigger that section is, the better, the more accurate your value will be. What we're going to do is try and find the graphs where it can be easily found. Won't easily find the change in y and the change of x. No point in trying to go like through half boxes because that makes it really difficult. So here you can see we've tried to pick the biggest one that gives us the simplest numbers. So I've drawn the red line to show our change in y over change in x. And then the difference here is 6 because that's 1 and 7, as you can see. And the difference here is 4 because that's going from, obviously from point, I think that's like 0.6, doesn't it? So we'll say 0.6, obviously going up to 4.6. So that's the change there, which is 6 and 4. So there you go. Yes, it was 4.6. So the gradient obviously is the change in y over the change in x, as you can see here. So the gradient is 0.67. Now the units for this is just that divided by that. So it's centimetres cubed per minute. That's always the units of a gradient. Look at the units on the actual graph. Okay, sometimes though we can get a rate of reaction and we actually get a curved line of best fit instead of a straight line, and we call this we call this a curved graph, but to work out the gradient we have to use a tangent. So you can see that we've got a curved graph here. Now this is a mass of a reaction vessel instead, and you can see obviously the mass of this reaction vessel is declining. So all we do is you draw a tangent, and a tangent is just a diagonal line that meets a curve at a very specific point. And all we do is then extend that line right across to the edges of the graph, up to the y-axis and the x-axis. And the gradient is basically telling you the rate at a very specific point on this curve. So let's say we're going to work out the rate of reaction at 3 minutes. So there's 3 minutes there. So we're going to put a tangent that just hits at that point there. So let's have a look. There it is. Okay, tangent just hits across there. We can see we've extended it right across the graph, and that's the tangent that we're going to be using. Now the gradient is just the same. It's the change in y over the change in x. So let's have a look. So that's the triangle that we're going to use. And let's put the numbers in. So it's 0.8 for the change in y. And it's 4 for the change in x. Now if we put that into our calculator, we should get a gradient of 0.2 grams per minute. Now again, we've worked out the units from looking at the units in the y-axis, which is grams, and obviously minutes is obviously in the x-axis down here, so it's grams per minute, and that's obviously the gradient. Okay, and that's it. That is a summary of the kinetics part for the ozone story topic for OCR salters. And please show your support for this channel. Everything on here is free. All we need you to do is just to subscribe to the channel. Just click on the middle button there and you get all the updates on the new videos that we upload. And also just a reminder that these videos are available to purchase. Great value for money, really help you to get that top grade. If you just click on the link in the description box and you'll be able to get them there. But that's it. Bye bye.